Okay, now we're going to take a look at some more complicated exponential and logarithmic equations, now that you feel pretty comfortable manipulating these. As a reminder, here are our laws, plus the change of base law, which we haven't looked too closely at, but have seen. It will come back again over and over. You have these in your formula book. You have them in your notes. I will need them. You will need them. Have them in front of you. But we'll start with one that's relatively easy, solving logarithmic equations. You obviously know how to do things like if I had log base 2 of x equals 4, you would be able to manipulate that because you understand what a logarithm is and its relationship to exponential equations. But if we have something a little bit more complicated with multiple logarithmic expressions in it, like this one, our goal is to first get it in the form of log base a of something is log base a of another thing, very similar to our simple exponential equations, because then we can get rid of the log base a's and just say something equals something else and solve it. And we're going to need to combine these then on the left side for now into one logarithmic expression, but they have the same base, so it's pretty easy. Using our log laws, remember, if they're separated as addition, they come together as multiplication. And don't forget as many parentheses as you need to make sure that you're using the distributive property appropriately. This is not just x plus 2 times 3. With the 2 times 3, it's the whole thing times 3. And then this is only one logarithmic expression, so that's, I think, nice and easy, one term. This argument, once I simplify it, is going to be 3x plus 6. And this is 27. So now, because log base 2 of something equals log base 2 of something else, that must mean that those two things are equal. So 3x plus 6 equals 27. And I know you guys are all smart enough to solve this quite simply, so we get x is 7. Okay. Going on to something maybe a little bit more challenging. I am going to ask you to draw on what you remember about quadratic equations because this is a hidden quadratic. There's no good way to come back and forth into doing these. We will see them again when we do quadratics. For now, I'll show you how we get a quadratic out of this. It sure doesn't look like it right now. But when I combine these two things, just like the last one, into one logarithmic term here, I get x times x minus 2 in parentheses. Again, the bases are the same, so I can do all of that. And this argument here is x squared minus 2x. And we can see this, this quadratic forming, and I can get rid of the logs. Just a very, very quick review of quadratic equations. Then I will leave the rest of all these different methods to when we get there. I do typically want to make them equal 0. So I'll pull over that x. So we have minus 3x, 10. You could use the quadratic formula. That's in your formula booklet. Whatever way you feel comfortable with. I personally like to factor, and I can see I can factor this well. We will go over it more in the future, but negative 5 and positive 2 are the things that will multiply to negative 10 and add to negative 3. And both of these when they equal 0, so x could be 5, positive 5, or x could be negative 2. But there you see my answers. If this were just a quadratic, but it's not. It's not just a quadratic. It's a logarithmic equation. So we'll come back to this after this reminder. Remember that the domain of logarithms, you have seen this slide, so you don't need to write it down again. It's fine if the whole thing is negative because that indicates a negative exponent or a rational exponent. That's fine. I guess rational is also fine here, or 0 exponent. But the argument can't be negative and it can't be 0 because it's not possible to have that happen. So when I come back to that problem, taking the two values that I got, I do need to check because it's not really just a quadratic. And if I put negative 2 into here, I'm going to get a big problem. Doesn't even matter if the other ones are fine. Okay, so this is actually not a solution. It's an extraneous solution. So x equals negative 2 is not possible in this particular case. It's not a possible solution here. The only solution to this is x equals 5. Okay. So when you have these kinds of equations, whether it's logarithmic or when we look at other kinds of ones like a radical, we do need to make sure that our solutions fit the original problem, especially if we take things out, substitute them in, rearrange them in some form. Always take a look and check it, not just to see if you're right, but to see if the solutions that we get actually work in the domain that we're given. We could also have something that doesn't quite look like it's log base a of something equals some other log base a of something. It's still not really any more challenging. I do want to still combine this into one logarithmic expression, and I'll show you then two ways of thinking about the rest of it. So using those laws, I'll take it a little bit slowly for now. This is log base 5 of 3 squared. Remember pulling that around? You could also, if you feel really comfortable, combine these two things in one step. I'll then combine them with the times into one logarithmic expression. That's 9, 3 squared. I can step over that, I think. So I now have log base 5 of 9x minus 36. Now, you could remember, if I just want to write this here, I'm only actually going to solve one of these methods. Remember that I could write this as an exponential equation as 5 squared equals 9x minus, that's a 6, 36, because logarithms solve for exponents. You could also say, well, I want to write this as a power of 5, or excuse me, as a logarithm with base 5, and you could do that and then get rid of the logarithms, making sure I know that the answer is 2 and the base is going to be here, so log base 5 of 25. That would then give me equal to 2, but I have the same bases there and can get rid of those. It's the exact same thing, what you see. So it really doesn't matter what you have. When I solve this and add 36 and divide, I get that 61 over 3 is equal to x. Okay, so adding 36, dividing by 9, and simplifying would happen with the same. Checking it, I do get positives in my logarithms. Obviously, that doesn't depend on x, so it's good to go. And now we have our maximally complicated e. They're not actually complex. These are not really complex. I really should have called them complicated because, at least for now, we're not having any complex numbers. I actually don't think we'll ever do logarithms with complex numbers, but I don't want to misspeak and forget something. So here are the steps. You don't need to memorize them. I do think it could be a good strategy if you can work through it, though. We're going to take the logarithm of both sides, expand, rearrange, condense it back up, and then solve it. It doesn't work for everything. Like there are some that we can't expand using logarithm laws. For example, if I have a plus inside of the logarithm, you can't just expand willy-nilly, of course. But the ones that we're presented with, if it's not a calculator question, are going to be like that. So maybe pause this and write these down so you can see what I'm doing. Otherwise, I'll just go ahead and get started. Maybe. There we go. This doesn't look that complicated, but it's still not a complex problem. There's no imaginary number. But what I do notice is I can't rearrange this so that the bases are the same. I can't just take the logarithm of 1 because I have variables on both sides. It is a little bit messier, even though the numbers are fine. And actually, I'm going to make this a little bit nicer for us. I'm going to make this a 2. There's no reason to make numbers difficult. So I'm going to take the logarithm of both sides. Doesn't matter what base I pick at all, so I'll just do base 10. Could say ln. You could pick any number. Pick your favorite number. Mine is 47, but I don't want to write 47. So, there. Now I've taken the log of both sides, and that allows us to manipulate things kind of down a step in our order of operations and make the exponents come around and the times go to addition and all that. So first I'm going to split up this term right here, this expression, into log of 2, separating into plus. There's no addition over here. I could have done the next step over here also, but now what I'm going to do is I'm going to bring around any exponents. The more comfortable you feel, the quicker you can move through the steps and kind of do them in the same step. I could have done all of that expansion in one. What you do need to be careful with, I'm going to purposefully write this wrong for just a second. This is the whole exponent. But if you don't write parentheses here, it's saying x minus 2 log of 5. But this whole exponent is actually being multiplied. So it is the whole exponent times the log of 5. And what we're going to need to do is expand that as needed using the distributive property. This one doesn't need to be. It's a 3. So x log of 5 minus 2 logs of 5. And now I want to move everything with an x to one side and everything without an x to the other, because I'll be able to factor out the x's when I have that. I'll move this over here, and then I'll move this one over there. Really doesn't matter which way at all. Actually, I'll move this one over to make positives. So that's plus, and then when I make this plus, so all my numbers are on one side, and I'll put all of my terms with x's on the other side. And what that will allow us to do is factor out the x. And from this very messy equation with powers and x's appearing on both sides, we now just have one x here. Let me write the rest. Okay, and I can now solve for x. Hopefully I am running out of space, but that's fine. We'll make it work. So the only thing over here is x when I divide. I'm going to divide by all of this. Just going to write a little bit smaller to make it clear what belongs to which. You have to divide by the whole thing. That is the full factor. And using the laws that we had before, I'm going to recombine this into log of something over log of something. I'm going to do it in one step. Of course, I need to bring this around as a power, so 5 squared, and that will come together as the 2. So 2 times 5 squared. And this is going to be log 5 over 3. And I'll just go over here now as I'm running out of space. So log of 50 over log of 5/3. You can't divide 50 by 5/3. They are stuck inside what is essentially the exponent part of our PEMDAS. So don't try to say, like, if this is 50 divided by 5, that's not gonna be fine. This would then be our final answer. You could, of course, if you wanted to, and the problem said to, write it as a different base. This does look like the change of base expression. You could say, well, this is log base 5/3 of 50. It just depends on what the question is asking you to do. But if it doesn't say to give it in any particular form, you are good to go.